Hello, everyone, and welcome back to 80 Podcast. And today we have with us Geoffrey Giles Stone. He is the author of the book From Where is the Rainbow? And if you haven't read this book, you might be missing a lot of things in physics. And today we are going to have some wonderful discussions in a lot of different topics, and we are going to have some fun as well. Hello.
How's it going?
Super good. Super fine. How are you?
Pretty good. I'm. This is my
Yeah.
fourth day here, I think, in Nepal,
Fourth day in Nepal, yeah.
and I'm acclimatized and comfortable. And you guys have been making me very comfortable. And I
Thank
really
you so
appreciate
much.
it.
Thank you so much. You got to experience some good summer, some nice monsoon as well in just 3 days. You loving it?
That was a monsoon. I had no idea. It seemed like a thunderstorm, but yeah.
Yeah, it's monsoon
Yeah.
going. Yeah, so that's why we are getting to eat mangoes here.
Oh.
We don't get off-season fruits here.
Mhm.
Whatever you get out of the farm, that's what we get here, and that's good, right?
I had 3 mangoes one morning. It was
So
delicious.
we have been talking on like different topics, discussing different aspects of physics. So I think to begin a podcast, topic like black hole would be the best. I'd love if you explain what is black hole in the simplest way that you can.
A black hole is a dead star. It's an extremely massive object squished into a small space. There's 2 parts to it. There's the singularity, which we think of as an infinite point of infinite mass, and there's the event horizon, which is a point where light can't escape, or nothing can escape.
Nothing can escape.
That's what it is, basically.
That's black hole. What makes it like so attractive to the physicists? We find them always talking about black holes. What's that?
Because it's so extreme
Mm.
and hard to imagine, and it's nothing. We haven't seen one real. We've kind of, we think we've seen them. We've kind of taken pictures, but that's only very recent that we've been able to get an image, actually. But it's just a very exotic kind of thing that's nothing like anything else we've seen. And because it's so extreme, it tests the limits of our knowledge. Like, we have to ask questions about what would happen inside a black hole or in the vicinity. It's a way to test our theories, or figure out what do our theories predict. And that's one way that we get a conflict between relativity and quantum mechanics, because they both have to apply to black holes, but how do they work together?
And the beauty of physics I see when it comes to black hole, I love that black hole was first predicted mathematically, right? And once it was predicted, then we humans, we imagined how it might look, how it might be existing in different parts of our universe. And after years, we got to know that it is real, and we even have a picture of it now. And we know that even our galaxy, the Milky Way galaxy, has a black hole in the center, Sagittarius A, right? So I think this makes physics very special, because we are predicting something so massive, something so extreme, that might be existing somewhere in the universe, and one fine day, we just see it.
Just as a personal note, I remember when I was a really young kid, I don't know, maybe 6 or 7, I remember hearing about black holes, and I was watching like Carl Sagan's Cosmos, right? And I really liked that. And thinking about things like time travel. And I remember being told that if you could travel faster than the speed of light, you could go backwards in time, right? And thinking, well, apparently the black hole can eject material faster than the speed of light. At least that's what some people thought at the time. And I thought, well, that would be one way to go back in time.
Yeah, we just need to reach the surface of black hole.
Yeah, that's all. Yeah.
So what is the most fascinating thing that you came to know about black hole, like in recent days?
Well, in recent
In recent days, like getting a picture of black hole itself was a very big thing, right? And we got to see how the curvature in space, as per Einstein's relativity, the curvature in space helps us see the backward end of the black hole due to the warp in space. We see something that is actually backward behind the black hole, and that also makes it special, I think.
Yeah, it's pretty cool. It's really neat to see the computer generated images. Like, yeah, it's like watching one of those like a tesseract or something, right? Like you see, your eyes don't know how to make sense of what you're seeing, right?
It's kind of cool. It's a kind of illusion. And talking like more about black hole, what do you think, like the event horizon itself? The event horizon is a point when beyond which we don't know what is happening with the black hole. Beyond the event horizon, we have made a guess that there is singularity, and singularity is actually a term. It's a mathematical term, right? It's a condition in mathematics when even maths have no answer, right?
I just realized I think I said infinite mass, but it's not infinite mass, infinite density.
Infinite density, yeah. Because it has infinitely small volume. That's why we get the infinite density from the formula. We have got the chance. We saw the movie Interstellar, right? Did you find anything weird in that movie, or it predicted it correct? What do you have any critique?
It was accurate according to the current science, as far as I could tell.
Yeah.
I don't actually think that gravity changes the flow of time. I suspect it might affect only, say, atomic clocks, but nothing else. So, for example, here's a good example. If we had a clock, say a pendulum clock here on Earth, and we have one on the moon, where there's less gravity, there's going to be a difference in the rate at which they tick.
Yeah.
But because the moon has less gravity, I have to make sure I get this right. So it'll actually tick slower.
Faster.
No, sorry. It'll tick slower because the way a pendulum works, it uses gravity to push it. But just like how an astronaut will walk slower, jump slower, the pendulum will tick slower.
Okay, yeah.
So time goes slower on the moon
than
it goes on Earth if we use a pendulum clock.
Yeah.
If we use an atomic clock, it's the other way around.
Yeah.
Then time goes faster on the moon and slower on Earth. I just say, well, we can pick and choose which clock we think is really measuring time.
Okay.
We don't have to automatically pick the atomic clock.
I see this as a very critical statement because it diverges from what we know about physics today. It diverges from the relativity itself.